Okay, good morning, everyone, and good afternoon, good evening for Eric. So Eric already here with us. So this is his last lecture with us. Today, he will deliver about the introduction to MCMC, Monte Carlo Markov chain. So yeah, I hope every participant here still stay healthy. And then if you have question, you can use raise hand, and also you can chat. You can write your question in the chat room. And then if you have any question or comment in the middle of a presentation, don't be shy. You can interrupt Eric's presentation. Okay, maybe Eric, you can start your presentation today.
Okay, thanks very much, Anton.
Yes.
Pleasure to see you all again. So I'm Eric Feigelson from Penn State. Oh, I forgot, I have to share. There we go. And I'm something called an astrostatistician, but I come from the astronomy side of things originally, not from the statistics side. But astrostatistics is the emerging field of study that sort of combines, it works on the interface between statistics and applied mathematics and computer science and astronomy. And the goal is to do a better job, or as good a job as we can, in getting reliable astronomical knowledge out of our data and making reliable astrophysical inferences from our reduced data. And the word reliable is sort of one of my favorite words these days, that it's not a question of right or wrong. I mean, sometimes there's some procedure that's wrong, but mostly it's a question of sort of the quality of doing things, that there's often a somewhat more better or more tuned or more general or more appropriate way of making some calculation than some other way that might be more familiar to astronomers. And the problem is that these good or better ways are buried in this huge field called statistics, and it's very hard to find them and to figure out what's going on. And so we need some people who are sort of scholarly in both fields. And there are these people now called astrostatisticians. And one of our jobs is to talk to all the other astronomers to try to help all of us to do a better job, because we do have some situations that are common, and although some of them are just individual, your project may have a very particular problem and you need a consultant, like a doctor when you're sick. You need a specialist consultant, and that's a good idea to seek out consultants. I started by going to the Statistical Consulting Center of my university to ask a question. And so we should all try to find ourselves statisticians who will talk to us for the more difficult problems. But a lot of things can be learned from just reading, believe it or not, there's a great deal of very reliable information in Wikipedia in statistics and applied math. It's actually quite good, but it doesn't teach you well. And so what I prefer sometimes are books. They write 100 books all the time, these statisticians, that are designed for graduate students in business or graduate students in biology. Well, why not for you? You could read the books too. Graduate students in astronomy and physics. So there are resources. In this particular topic, the best resource is a thick book. I don't have a copy here, called The Handbook of MCMC, of Markov Chain Monte Carlo. It's a big, thick book, about 800 pages. And it's edited by the most talented and written by the most sort of experienced and creative statisticians in the field. Often they created, so the chapter on reversible jump, MCMC, is by the statistician who invented it 30 years ago. And so you get these review articles. That's quite a lot of information there. And far beyond what I can do today, or what I know myself. Okay, so let's get started. And sort of my way of teaching sometimes is to not start where you want to end, but to start sort of at the beginning. So I'm going to start off with some slides that discuss some fundamental issues of what are stochastic processes in general, and then we'll get into Markov chains as a particular kind of stochastic process. And then we'll finally see how Markov chains can be used for Bayesian computations. We discussed Bayes' theorem and some of the applications yesterday. In particular, these two types that are fundamental to MCMC calculations. And then I'm going to review others. And we have a great little app that we're going to look at that's really fun to do. And then we're going to discuss a problem, a difficulty with MCMC about convergence. And then I'm going to give you my advice, whatever it's worth. Now, just to warn you, I am actually not an expert on this topic of astrostatistics. I don't do it much myself. I do other things myself in my research. But nonetheless, I do teach this kind of stuff. So I'll teach it to you at a sort of in lower intermediate level. For advanced, you should go to other scientists, maybe your other instructors here, who will teach you more detailed things and maybe more reliable. Okay, so let's see now, what are stochastic processes? So I have a couple slides. Basically, stochastic processes, let me phrase it differently. Basically, most measurements astronomers make can be viewed as stochastic processes because we rarely make one measurement. Sometimes we go to one star and just measure its brightness once quickly, and that's not a process. That's just a single measurement. But more likely, we sit there and we measure something over and over again, or we sort of go through an image and ask questions 1,000,000 times about the image, or other things. So let's just see, for instance, just the concept of brightness. So brightness as a function of right ascension and declination in the sky, an image. That's an astronomical image. And that can be viewed as a stochastic process. Brightness as a function of wavelength is what we call a spectrum. Brightness is a function of time, we call a light curve. Doesn't have to be brightness. How about radial velocity as a function of time? That might be considered the motions of the orbit of a planet around a star. How about something a little more theoretical, from theoretical astrophysics? What about the density of a fluid, of a compressible fluid, as a function of 6 variables, location in 3 dimensions and velocity in 3 dimensions? We call that phase space. And so that can also be viewed as a stochastic process. So the main thing is that these are functions of time-like variables, fixed variables like the fixed pixels in an image, or the fixed pixels in wavelength in a spectrum. So that's the critical point here, is that it's not a question of measuring brightness as a function of, I don't know, metallicity or something of some objects. sort of repeated measurements along fixed axes. And time is often one of those axes. Not always, but it can. Okay, so random variables, brightness, radial velocity, density are random variables, are functions of, it could be either a continuous time-like variables, or could be discrete, either because it's actually discrete or because we pixelate it for convenience, because it either comes out of that way from the detector or it's just convenient. The radial velocities themselves can be discrete or continuous values. So discrete might be, for instance, photons, counting photons, or accounting some sort of events or the arrival times. The continuous variable would be something like brightness that can have a real values. Okay, so we now have sequences of IID random variables. This is the way statisticians talk. Independent and identically distributed random variables. Okay, and they can be IID, but they can also exhibit dependencies. For instance, the point spread function of a telescope on an image means that there's dependence of adjacent points if there's any brightness coming through the telescope. Or it could be dependence from the underlying astrophysics of it all. For instance, the brightness of an accretion disk or a pulsating star cannot change, crazy instantly. There's a physical object there, and it can only change slowly in some organized way, and so we would get dependencies. So a pure IID process is like Gaussian random noise, and it's very simple, and there's not much to do with it in terms of analysis. So we're going to talk mostly about random variables that have some sort of structure in them, some sort of dependencies, depending on previous values, or depending on neighboring values, or depending on some external variables. Okay, now here's a piece of a vocabulary lesson. The word is stationarity. So a stochastic process is stationary if, when you have a series of measurements as a function of, I'll use time, but it could be space or something else. It's a function of time, and then you shift it, to a different time, or you look at a different part of the image, that you have the same distribution. The distribution of the x's, the histogram essentially of x values, is unchanged in different parts of the data set. That's called stationary. Non-stationary means that there's trends, let's say linear trends, or things get brighter as a function of time in an organized way, and that's a non-stationary phenomenon. Okay, so the spatial structure of an image that has stars and galaxies is non-stationary, because over there's nothing but dark sky, but here there's a galaxy, so it's not stationary. The brightness variation of a variable star. Well, that's more complicated. If it's stochastically variable in a constant, let's say periodic, so it's always the same period, here, here, and here, then it's actually stationary. It's a stationary periodic phenomenon, or even stationary, sort of like an accretion phenomenon, might be stochastic. Or it could be non-stationary, something crazy, something different, like a flare or an explosion, definitely is non-stationary. So stationarity sort of affects things, and we'll be talking mostly about stationary processes in the next hour. Okay. Now, what if your random variable it has the particular characteristic of having non-negative integer values, like 12 or 17 or 2 or 0, just not -7, and not a real number. Okay, then it's called a counting process. Okay, and we have counting processes in astronomy. Okay, and if a counting process has the following properties, it's called a Poisson process. When the values at adjacent times are independent of each other, for any sort of spacing, even close by, they're independent, okay? And the number of events, the number of events in some interval of time, here's the interval of time, there's the number of events, will, if you look at it many, many, many times, it will have, you can do a histogram of it. The histogram will follow this function here, which is not very obvious, okay? But it basically starts low and goes up high and comes down, but it's an asymmetrical function. And it only has values at 0, 1, 2, 3, 4, 5 at integer values. Okay. So that's a Poisson thing. And that, of course, is the Poisson distribution. So it ends up, and I'm not going to read this page entirely, but the Poisson distribution and many other distributions, the other famous one is the Gaussian distribution, have mathematical properties. So the expected mean value is just lambda times the length of time. And actually the variance is also lambda. That means the standard deviation is the square root of lambda. And the distribution of inter-arrival times is actually exponential. These are properties unique to the Poisson process. So if you have, sorry, it keeps on doing this, two types of events with different probabilities, let's say you have two kinds of counts, let's say high energy and low energy or something like this, red or blue or something like that, okay? Then you have two independent Poisson processes with this sort of mixing ratio. If it's stationary, okay? A stationary process has lambda is constant. So it has a constant. Lambda is often called the intensity of the Poisson process, okay? And if it's non-stationary, it's called either a non-homogeneous or inhomogeneous or non-stationary Poisson process. Interestingly, the sum of independent Poisson processes is a Poisson process, but the difference is not. Because if you take the difference between, you can go negative. Actually, that has another distribution. It's called the Skellum distribution. Most astronomers don't use that, but they should. When they take, let's say in gamma ray astronomy, you take the integer number of counts and you subtract the integer number of background counts, then it's a Skellum distribution. It's even fatter than the Poisson. Okay. And it could be that the rate itself depends on something else. It's a function of something else. And you may know that function, you may not, you may be able to measure it, you may not be able to measure it. It depends on the situation. Sometimes the science is actually understanding how the Poisson process changes. Okay, so now let's talk about something called a Gaussian process. So when you have a Poisson process and the n is very large, so the n is approaches infinity, then the distribution of the Poisson process becomes symmetrical, and it resembles a bell-shaped curve called the Gaussian curve. And now we have a Gaussian process. So this, of course, now applies for not just integers, very large integers, but for real numbers. Okay. So this process, which I've sort of defined here, is sort of a simple version of it, has zero mean and a variance of sigma squared, and we normally pay attention to the square root of that, which is the standard deviation. So x is normally distributed, and if you have a limit of this particular one here, of this sort of going left and right and left and right and left and right, it's called a Brownian motion process. And if you have instead of constant jumps but fractional jumps, then it's a geometric Brownian process, and you have a log normal distribution. And if you change it again, it's something called the Brownian bridge. I'm just sort of saying that there's all sorts of varieties of stochastic processes that have certain mathematical properties, okay? So a stochastic process is a Gaussian process if the values of the random variable have a normal distribution at all times. And it's a stationary process if it is the same at different times. And there's actually weak stationary and strong stationary and stuff like this. And let me just mention that it doesn't have to be stationary at all. It doesn't even have to be Gaussian. Okay, but in particular, if you make fractional changes every time, based on that you change some fraction with respect to the previous value, it's called a first order autoregressive process, AR1 autoregressive. Okay. And if it depends on other values, n-2, n-3, n-4, then it's AR with it can have what's usually nicknamed of order P. You have dependencies on P previous values in time or in space or whatever it might be, is your time-like variable. If you have a stationary process that has a Gaussian noise, but the values actually also depend on, also depend on previous noise values, then it's called a moving average process, or MA. And combining that is ARMA or ARMA. And there's many generalizations. There's ARIMA for non-stationary autoregressive processes. ARFEMA has long memory, power law parts. GARCH has volatility, not a constant sigma squared, but itself is an autoregressive process, and goes on and on and on. There's all sorts of complicated ways of defining Gaussian processes that have dependencies that are not stationary. Some are stationary, some are not. One of them is called the Ornstein-Uhlenbeck process. It's actually used in hundreds of astronomy papers to model quasar variability. But it's usually not called this. It's usually called the damped random walk model, which is okay, but if you use that language, you're not connecting well to the literature and the understanding, the mathematics of stochastic processes. So this is all developed 100 years ago, okay, by mathematicians, and actually physicists and economists played major roles as well. Okay, so now, why are we going to talk about something called Markov chains? Okay, so a stochastic process is Markovian, or is a Markov chain, if the distribution of the next point given the previous points depends only on the single most immediate past value. n+1 depends only on n. You don't have to have any memory that goes back to order P. Just order 1, like MA1. That's a Markov chain. Random walk. The random walk, you take a step, you close your eyes, you turn around, you take a step in some direction. Then you close your eyes, you take a step in another direction. That second step depended only on where you were the past time. And you zigzag through the space in a random walk. That's an example of a Markov chain. That's actually MA1, the physicist one-dimensional random walk. So here's something a little more mathematical. This is the way the statistician would write it. It's a little sort of, I don't know, it's complicated. So if the probability of the n+1th value is equal to j, given that the nth one is equal to I, and the n-1, it goes on like that, is equal to this probability here, and this is a matrix essentially. Okay, so the values that it can take are called states, and they can be integers, they can be real numbers, they can be what they want. And here's the physicist random walk, very simple one of the Markov chain. Okay, so this matrix of transitions from one value to another value, these are conditional probabilities, going back to the probability theory that Tri and I mentioned to you, discussed with you on the first day. Okay. So you have to define an initial state at time 0 or location 0 or wavelength initial or whatever. Okay. And it's possible that this ith state doesn't communicate with all of the j states. Some of the elements in the matrix could be 0, and others could be filled. So constructing Markov chains, I don't know quite why this is happening. Okay. Very often we use random numbers to generate IID sequences of values, but the Markov chain using this matrix of transition probabilities adds these non-random characteristics to it. Okay, that it's correlated with the past, very much like the random walk. It has a correlated motion across the space. So when we combine sort of random numbers with the concept of a deterministic Markov chain, then we have something called Markov chain Monte Carlo. So it's combining deterministic stochastic process with a random stochastic process. Okay. So it's sort of a rather particular thing. Okay. And you sort of think, why do I have to learn this sort of mathematics, applied math? You know, it seems like it's so relevant to data analysis or data modeling for astronomy, but that was actually very interesting. It was not obvious for many, many years. People knew modeling problems, likelihood-based modeling problems, including Bayesian inference problems, and they knew about Markov chains and Markov chain Monte Carlo techniques, but no one put it together for about 30 years. From the 1960s to about 1992. Nobody connected this. They just didn't know about it. They'd never thought about it. So it's not really obvious that this kind of mathematics is relevant to statistical calculations. Okay. So why don't I stop there? Shh. There's a dog there. Excuse me. Why don't I stop there? I've spoken now for a little bit. And are there any questions about stochastic processes? Hold on. Well, no, I wouldn't do it. I have a big, thick book. It's all about stochastic processes. It's an entire field of mathematics that takes a whole semester to learn well, and even more than that. It's often engineers who study stochastic processes and applied mathematicians. Any questions or comments about stochastic processes and Markov chains being a particular kind, and not a very simple kind, that combines IID random noise with deterministic autocorrelated noise involving the recent memory?
Okay. While break, is there any question or comment from the participants here? Okay, let me check if there is. Oh, there is no question for break. Yeah,
I'm not too surprised because it doesn't seem obviously interesting to an astronomer. Okay. Okay. So this is now going back sort of to what I was talking about yesterday, that Bayesian computation of the Bayes' theorem of studying the distribution of the likelihood times the prior distribution sort of everywhere over a high dimensional space, or maybe some low dimensional one, but over a multivariate space, is often a difficult thing. Okay, So, and for maximum likelihood estimation, MLE, what we want to do is climb the hill and find the peak. And that's an easier problem than mapping the whole structure, the whole posterior space. It can be quite time consuming. There just could be too many pixels, too many dimensions, too many locations to map it well. Okay. So what they realized around 1992 was that Markov chain Monte Carlo methods can map the posterior by drawing samples that start somewhere and then just make one step and then another step and another step from there and another step, only remembering the previous location with a certain randomness, random direction, and maybe random leap. But it's not entirely random. They have rules. They invented rules for the jumps. And the rules were trying to help us in higher dimensions to map out a nonlinear function. In this case, it's the posterior of Bayes' theorem. Okay? To efficiently map and locate maxima in high dimensional parameter spaces. So it wasn't obvious that Markov chain Monte Carlo could do this, but that was in fact the discovery. Okay. So just a reminder that for simpler problems, where let's say there's only one peak, then you might, and not too disturbed and too bumpy, you can do it much more easily with INLA. And for MLE, you can do it much more easily with the EM algorithm. And you don't have to use MCMC, but you want to use it for more complex problems. Okay, so now let's see what they're actually doing with this sort of mathematical foundation. Okay, so one of them is called the Gibbs sampler. It actually doesn't seem to have anything to do with Gibbs, but whatever. And this is the 1950s. So, well, this one's the 1950s. I don't know when this one was. Okay. So the issue sometimes is that you just have all these dimensions, and how do you jump around in so many dimensions? So let's consider a three-dimensional parameter space, theta 1, theta 2, theta 3. These are the parameters in the model that I talked about before in Bayes' theorem. Okay. So you got to start somewhere. Okay. So let's start somewhere with the 3 vector of some starting location, make a random step. Okay. And then calculate the numerator of Bayes' theorem, or whatever you want to calculate, whatever function you want to calculate. For the new value of the first variable, holding the other ones fixed. And of course, you have your data. Okay. And then make another step in the second variable, holding the first one and the third one fixed. Notice the first one's already been updated, but the third one hasn't. And then update the third dimension to its new location, holding the other 2 fixed at their new location. And now you've done 1, 2, 3 in X, Y, Z. You've made a step in all 3 of them, but you made the step one by one. And that's it. That's the Gibbs sampler. That's the concept of the Gibbs sampler. Okay. That now you've made one step. It took you 3 calculations to do it. And now you can make another step. And first 1, 2, 3, and 1, 2, 3, X, Y, Z, X, Y, Z, X, Y, Z, and you can go around 3-dimensional space in this way. Okay. So for very high dimensional problems, there's some tricks. You can block, take, let's say there's 30 dimensions. You can take, 3 blocks of 10 of them and do for the first 10, the second 10, the third 10, each having its own Gibbs sampler. And there are other tricks to play to deal with sort of more complicated problems. But it's a completely reasonable and logical approach. In fact, believe it or not, the EM algorithm that's so famous in likelihood theory calculations is actually a Gibbs sampler as well. Inside of it is a Gibbs sampler. So this is a very reasonable, intelligent thing to do, to simplify, have simple procedures for a more complicated problem. But now comes the question of improving the efficiency, just running randomly around this space. You might start off on the edge of the beautiful posterior peak, and you might randomly go off over there where there's nothing going on. You want to actually map the interesting part where the likelihood is high to find the maximum in its vicinity. So we want to sort of increase the probability that we're climbing in the right direction. Okay. So the Metropolis-Hastings algorithm, this was developed in the 1950s by, of all people, by physicists doing chemistry. Okay. You make a random step, but you sort of look at it, and if it doesn't increase the posterior, don't go there. Stay where you were and make another random step. And only accept it if you like it. And that way you don't climb down the hill. You look around and where you are and you try to climb up the hill. And I'll show you the math behind this in a few minutes, but this is the Metropolis-Hastings algorithm and in the 1950s, and I think Hastings was the 1970s. Okay. So this was all being developed by other people for other reasons in science and applied mathematics, and nothing to do with statistics at the time. But these are the Gibbs sampler and Metropolis-Hastings algorithms for Markov chain Monte Carlo calculations. Throughout all of this, we're using the concept of taking where we are, taking one step, and then forgetting it, and then one step and forgetting all the others behind, and climbing in that way. That's the Markov chain property. And the Monte Carlo property is the randomness of where we're going and using random numbers to make progress instead of deterministic numbers. Okay, so one of the very important issue for all optimization and numerical simulations of this type is convergence measures. Where am I getting where I want to go, and have I got there? And when do I stop? The stopping rule. And unfortunately, there's no theorems at all guaranteeing convergence in MCMC, all of MCMC. So in practice, you actually might need to do it millions of times. Okay. And you might need to have many chains because you might have started in a bad spot and you just sort of stuck and you can't get where you want to go. Okay. So common stopping criteria include the chain sort of converges on itself, that the autocorrelation within the chain becomes small, and then if you have multiple chains, that the within chain and between chain variances approach the same number. And with these concepts of Markov chain, Monte Carlo, Gibbs sampling, and Metropolis-Hastings algorithm, there are dozens of varieties of algorithms that have developed over 20 or 30 years, and they're implemented in many, many sort of places. For instance, in R, there's dozens of them implemented. Okay. Now, two of the variations of this have become sort of famous in astronomy, and rather suddenly, okay. And it was really sociological, not scientific. It's famous because it was done by other astronomers, okay, and they knew about it. But in fact, there are dozens of them. So here is a list of A through Z, but I didn't have space on this, of one package in R that gives you a sense of how many different MCMC approaches there are. There's adaptive Metropolis. So adaptive probably means that it helps you decide whether to take small steps, you're getting close, or big steps. There's Metropolis within Gibbs, and is it here? Gibbs within Metropolis. Is it somewhere in here? There's hit and run Metropolis. There's delayed rejection. There's delayed rejection adaptive Metropolis. There's a simple Gibbs sampler. There's a gritty Gibbs sampler. Hamiltonian Monte Carlo actually has mathematical relationships to Hamiltonian mechanics. It's a theoretical view of mechanics in physics. Okay. And this is just some of them. There's really many more. Okay. There's one here. This one, an affine invariant ensemble sampler. Well, that one has many you have many chains going at the same time. They sort of pay attention to each other, And if one of them is climbing nicely, the others listen, and they all sort of join go in that direction, which is very clever. It's very clever indeed. And the word affine invariant means that the dimensions could have different scales. Maybe one scale only goes from 0.01 to 0.1, and another scale goes from 1 to 1,000,000, and it doesn't pay attention to the scales. So this particular one has become rather famous in astronomy because of these good properties. That's this one here. Okay. It's actually fairly new. This one didn't come out until 2010. It was published in Communications and Applied Mathematics and Computer Science in a math journal. Okay. And so you actually run thousands of chains, and each one's called a walker, and they're all based on scale distances, and they pay attention to each other. And what's wonderful is that this young astronomer named Daniel Foreman Mackey in America, with Professor David Hogg and Dustin Lang. I'm not sure who Goodman is. Oh, Goodman, there Goodman is. Goodman was the mathematician. They wrote a lovely code in Python that implemented this called EMCEE, which sounds like MC, like MCMC. So this has now been used hundreds and hundreds of times because it's a beautiful code. But from our perspective here, it is one. It's this one. It's one of the many MCMC algorithms. Another one a few years earlier, from 2008, was done at University of Cambridge in England. Professor Mike Hobson and then student Farhad Farouz. Very brilliant code, very brilliant people. Okay, they use something called clustered nested sampling. Sorry, to improve the procedure. And their particular code, which is called multi-nest, it nests for nested sampling. It's one of the ways of doing Gibbs sampling that's sort of more intelligent in some cases. Multi, we refer to multi-peaks, is particularly good for you climb up a peak, but oh, there's another peak over there that might be taller, and it knows how to jump around fairly intelligently. Even in high dimensions, it's not perfect, but it's pretty good. So it was written in a very fast language called Fortran, and it has implementations in other more popular languages. Here they are. So these are the ones, there's hundreds of citations to both of these. And everyone thinks that many people think Farouz and Hobson and Foreman Mackey and his colleagues invented these methods, but they didn't invent them. They're all here. These are variations of those methods, implementations of them, but designed for astronomers in a very nice way. Okay, so I want to end this. I hope this works. So this might take me a minute to get settled. This is a wonderful website. So let me see if I can show this to you. Okay, so I'm going to stop sharing this, and I'm going to share this instead and see if I can get it to work for us. Okay. So what this is, it's a Java app or something like this. It's some sort of an app that illustrates some of the MCMC methods. So in this case, I said, start with a banana shaped, a curved shape in 2 dimensions, 2 parameters, that's peaked in the middle of the banana. And try to map out the entire distribution, and these little dots, these little gray dots represent the effort to map it out. Let me go a little faster. You can see that actually the Hamiltonian MC, that's the one we're doing, is quite sophisticated. It has these wiggles and it's wiggling around. It has complicated mathematical rules. Let me go faster. There we go. And it's slowly building up quite nicely the distribution of the banana, but it's taking many, many hundreds of thousands of, or even millions maybe, of iterations to build up a good representation of the shape that we're looking at. Isn't that cool? It's a great app. Let me try a different one. Let me try a multimodal. So this one has 3 modes. You can see they're completely separated. So the algorithm has to know how to jump between them. You can see it's done this one nicely, but it hasn't done the one on the lower left very well yet. So we'll see if it does it. You see, it got too many there, not enough there, and not nearly enough in the bottom. But it's slowly doing better. Okay, so this is one of the most sophisticated of the algorithms. Let's look at a simpler algorithm. Let's just look at a random walk Metropolis Hastings. Okay, so let's slow it down for a moment. So now it's just looking in a circle. It's going in a random direction, often the wrong direction, so it's less efficient in mapping out the peaks. And just depending on the size of that circle, well, it may or may not jump well between the modes. So this is a rather traditional one algorithm. Let's take a look at nuts. Nuts means no U-turn. Don't ever turn back. So this one's actually a fairly famous one. And it's doing a good job, but it still has trouble jumping correctly, efficiently. Let's try another pattern. I've never seen a posterior look like a donut, but they have, some of them do this well and some of them don't. Let's not do a donut. Let's do, what's a funnel? Oh, okay, a funnel. Okay, let's look at a Gibbs sampler. You can see it's doing square things. It's doing each variable separately. And so it's not going at angles. It's going only in X and only in Y and making right angles. And so this is the most primitive Gibbs sampler. But even a primitive one will eventually do a job if it's not too complicated. Okay, how did you like that simulation? Isn't that cool? I think it gives me an intuitive sense of what MCMC does and an idea of what the different kinds of algorithms do. Some are square, some are round. Those are the simple ones. The more clever ones have very fancy rules for squiggling around, and they can be more efficient. Awesome. Yes, I think it's awesome.
Okay, so, maybe you have one question in chat room.
Okay.
So, Annie, do you want to ask directly to Eric? No. So yeah, he is asking about what is the differences between Markov chains only and Markov chain Monte Carlo.
I think, believe it or not, I'm not sure my answer is correct, okay? But my understanding is that a Markov chain doesn't have random numbers in it. A Markov chain, you start somewhere and you have these fixed matrix of probabilities of doing things, and you have to make you start somewhere, you make one step, and the rest of it is deterministic. So it's rule-based, based on the memory of where you were before. But the rules are deterministic. It's like a formula, okay? It tells you where to go. The Monte Carlo, you throw dice, you get random numbers. And the random numbers sort of say, well, we'll change direction, or oh, we'll change the size of the step, or oh, we'll find the probability of going there instead of there. And so the combination of random numbers with Markov process is called MCMC.
Okay. Is there any question from participants? Maybe Nimas, do you want to ask something?
Yes, but I think Lognum can first ask question.
Sorry?
Lognum in participant.
Yes, so
Okay.
can you hear me?
Yeah, please
Okay.
go ahead.
Hi there.
Okay, Professor Eric, I have 3 questions. And the first one is, how gives sample play a role in Monte Carlo method? The second one is Martinez is some kind of tree algorithm. And the last one is how Hamiltonian MCMC, what is Hamiltonian MCMC? I mean, what is it related to something about Hamiltonian or something like that?
Yeah, I didn't quite understand the questions.
Can you repeat again, Lagno?
Okay.
Slowly.
Okay, sorry. The first one is how give sampler play a role in MCMC?
How do we do what in MCMC?
Give sampler.
Keep what?
Give sampler that you explained earlier.
Yeah, the sound is not good enough. I'm not quite sure.
Oh, sorry about
Anton,
that.
About GIP sampler.
Give
Eric,
sampler.
GIP sampler.
Oh,
yeah,
Gibbs. Gibbs.
Give
the
Sampler.
Gibbs sampler. Okay.
Sorry.
Okay, the Gibbs sampler is basically a technique of simplifying a multivariate problem to a univariate problem, to a long sequence of univariate problems. So it's just a strategy for simplifying the calculation. And as you saw, people don't use the naive Gibbs sampler anymore. They use these more complicated ones. But often there's a Gibbs sampler sort of inside of the complicated ones.
Let's see. So it is just a method.
It's just a method. It's just a numerical method. All of this are just numerical methods. There's no statistics in it. There's no astrophysics in it. It's just a way of calculating posteriors with difficult likelihoods and high dimensions. It's just too hard to figure it out otherwise. The easiest thing would be to just make a grid and calculate it on the grid and smooth it, and then you've got it. But if you're in 20 dimensions, the grid's too big. So these are ways of sort of zigzagging your way around and sort of gradually building it up.
Okay, I see.
And that's what we saw in the simulation. Now I didn't turn it off. It's still doing a Gibbs sampler of a funnel. So as you can see, after a long time, it's beginning to map it fairly realistically. It's getting the peak very nicely, but the more diffuse regions, it's not doing yet very well. It's not getting them so well over here. So maybe I'll need to run it for another hour or maybe another day. I don't know. That's one of the problems. One of the problems is that it's difficult to know how long to run these things.
Okay, Lagnum, is there any question? No?
Okay, and I will skip the second question, and the last one is, what is Hamiltonian MCMC, and how is related to Hamiltonian or something like that?
Yeah, I can't explain that. I'm sorry. I'm too dumb. Okay.
Sorry.
There are people who understand it better than I do. But it's fairly sophisticated. It's not easily explained. Okay, let's now learn some more details. Okay. So,
Yeah, thank you very much.
thank you. I'm sorry I didn't answer very well. Okay. There's different aspects of MCMC algorithms, you know, how to choose between them or how to tune one of them. Non-Markovian ones sort of violate the rule that you're only paying attention to the previous value. For instance, the ones that are adaptive, they pay attention to this, to sort of how things have been going, and that actually can speed things up, but they're non-Markovian. Recurrent means that it tends to go back to the same location, which is a bad thing because you often get in circles. It comes back, or it could be periodic. What you really want is an irreducible one where it can reach anywhere in the space, and then of course chooses wisely. Then there's a theorem called the ergodic theorem, which is powerful, but it only applies to a certain kind of Markov chain that is stationary, aperiodic, and irreducible. So under certain limited conditions, there's a theorem that says that it does converge, and the central limit theorem of sort of a Gaussian distribution of convergence applies. So if you have an ergodic chain, then maybe you have criteria for stopping. But most of the chains are non-ergodic, or many of them are not. And then you don't know. The fancier ones, I think, are not ergodic. Okay. You need some way of starting and some way of sort of proposing sort of how to proceed. Okay. Particularly with the Metropolis Hastings, you need to decide on an acceptance rate, like someone once said, it's best to accept 23% of your original choices. And they now feel that that number is not fixed. There's no best acceptance rate, but you do have to choose one to be, you know, either more generous so that you accept more of them and there's fewer calculations, but you might be going in the wrong direction, or accept only a small fraction, then you spend a lot of time sitting there trying to find the right direction, and then you make a leap. It's a better leap, but it took you longer to make it. And then how to block variables, if this only applies to high dimensions, and interblock correlations can get fairly confusing. So there's sort of different aspects to this. Now, let's actually look at the Metropolis Hastings algorithm, which is the original one proposed in 1953. So we have a function y of some time series or time-like series x, and we want to construct a sequence of y's that sample our posterior or target distribution. So you actually have to invent a simpler function that is sort of bigger, that has the posterior inside of it, q. And the simpler one is much quicker to calculate. Okay, and you make this this choice that if this quantity here is smaller than one, then you jump, and if it's not, then you don't jump. And this is the kind of way that these decisions are made. It's a probabilistic decision. And if it's accepted, then you jump and you've gone to t+1, the next step. And if you reject it, you do nothing and you try again. Okay. Under this condition, the samples are independent. In this condition, we have a metropolis random walk. There's sort of different situations. Now, the stopping rules are very important because eventually you have to stop. You know, we're still running that funnel calculation, and I don't know when to stop. And there's no theorems. And oh, I already said this is the general things. Now I'm going to give you some details about this. Okay, so this is one of the stopping rules. Okay, when the MCMC, when the chain reaches, you have to specify a sort of a minimum scatter, a sigma essentially. Then you can do it, but because it's autocorrelated, you don't quite know what n to use in this calculation of the standard deviation. This is the usual calculation of standard deviation, but n is sort of wrong. So there's different suggestions of how to correct it. This is a statistical matter. So Geyer is a statistician who invented this particular one. And as you can see, it's a little complicated. It involves some calculations here, involving correlations here, and you sort of have to jump through this sort of several calculations to estimate it based on the autocorrelation function of the chain at that time. The one that's most popular in astronomy and elsewhere as well is the Gelman-Rubin diagnostic. Gelman and Rubin are also very distinguished statisticians. They developed this in 1992 when the statisticians realized this is wonderful, but they needed a stopping rule. So now the rule has to do with that the chains have sort of forgotten their starting values, and that the recent output of different chains are indistinguishable. So all the chains seem to have converged. So we have a within chain variance and a sum of within chain variances and a between chain variance, and you want them to converge. And so this is the ensemble variance and the diagnostic that they recommend that should approach 1.0 when you have converged, involves this R, that's the diagnostic, should be 1. There's the dimensions of the problem. There's this W, and that V is defined over here. So it really, and that D is defined over here, and this defines the R. So these three equations define sort of a criterion, and you go along and you let these things iterate, and you every once in a while you stop and calculate R. And if R gets close to 1.0, then you maybe have converged. And that's the famous Gelman-Rubin diagnostic. But there's a whole bunch of others. Here are the 5 most well-known ones. Gelman himself has other suggestions. Raftery is another distinguished statistician I know, and I'm not sure who the others are. These are, R has several powerful packages for not only for doing the calculation, but for providing graphics and calculating the diagnostics to help you with convergence. After all, if it's just not converging at all, you want to know before you spend too much computer time, and now you should stop it and start again, do something else. So these are CODA and BOA in particular are very widely used among statisticians and the people who use R. So let's talk about the graphics for a moment. Astronomers tend to make 1 or 2 of these graphic plots, but sort of not all of them. One is just to smooth the Markov chains and to see if they have sort of large-scale structure. So that's kernel density estimators or smooths. One is to just plot the values of each variable in a chain. There's a lot of plots, a lot of information there, but that's essentially the raw data. Perhaps the autocorrelation function of each variable in each chain is a little simpler, and it should go down to something consistent with 0 to show that the autocorrelations of the chains have stopped when it converges. And cross correlation plots that you do the cross correlation of the 5th parameter chain with the 7th parameter chain to make sure that they're also approaching each other. But there's a lot of other plots. It's a whole bunch of them, okay, that most astronomers don't know about, but they're all provided in these R packages and probably elsewhere as well. So there's a general opinion among statisticians who are much more expert than I am that it's important to do a lot of checking. Don't just look at the Gell-Mann-Rubin statistic once and say, oh, it's just 1.0. You have to look at the fluctuations in this plot, and you have to stack this plot, and you just want to look at different things. For simple problems, none of this matters. For simple problems, you could just use a grid. Okay, you don't even need MCMC at all for simple problems. You can use INLA, which is a well-known approximation, very efficient. But for more difficult problems, then it may be wise to be more cautious and to look at different graphics and different diagnostics, not just one graphic and one diagnostic. So MCMC, I counted in the ADS system, is used in 2,000 astronomical papers, and it's doubling every 6 years. Most of the astronomers using it use one algorithm, usually one of the ones that I mentioned, the 2 that are popular. Okay? They usually do little convergence testing. Maybe they say, oh, the Gell-Mann-Rubin statistic is 1, and that's all they say. Okay, so here's what one of the founding statisticians warns. It's just him talking. He says, MCMC is really great stuff. It often works and does problems nothing else can do. But in complicated applications, we can never be sure it worked. Simulations are notoriously hard to test and debug. How can we tell when the random output having an unknown distribution in a black box MCMC is wrong? And then here is an interesting list of papers and even books on MCMC type Bayesian computation. And most astronomers are just doing one thing once quickly and assume it's okay. By the way, the 2,000 papers are not all Bayesian. Not really Bayesian. Astronomers sometimes say it's Bayesian, but really they're doing chi-squared. It's really a chi-squared function they're estimating, or a likelihood function. And sometimes they're doing a true Bayesian, and it's a posterior. By the way, MCMC could be used for all of them. MCMC can be used for any purpose, nothing to do with statistics. You could use it in astronomy and astrophysics for sampling distributions with formulas. You need a model, a likelihood. No, you need a function. It doesn't have to be like that. So I'm actually getting close to the end. I'm going to end a few minutes early. So now we're going to say, oh, wait a minute. How's it going? There we are. Is it getting better? Slowly. This was not one of the smartest algorithms. And so it's pretty slow and getting better and better. Let's see if one of the other ones does better. How about efficient nuts? We'll let this one run for a few minutes and see if it does it faster. Excuse me. Okay, so these are sort of my thoughts. If you have Bayes' theorem and you have a likelihood and you have priors, and if it's unity prior, you just might as well do EM, you might as well just look at the likelihood and do MLE. But if you have complicated priors and complicated functions, you have to go through this process of Bayes' theorem and mapping out the posterior in high dimensions. So but when you have so if it's simple and it's just a simple likelihood and the posterior or the likelihood as a unimodal structure, just one peak, then you might as well run EM algorithm with maximum likelihood estimation. It usually converges in 100 iterations or something like that, and it has theorems of convergence, but you can still use the MCMC results if you want to. So for very easy problems, it's fine, but you don't have to do it. And a lot of astronomers are running it for very easy problems. For what I call easy problems, you have informative priors, and you want both the best fit, but also you want to see the shape of the shape of the posterior around the best fit. But it's still just one peak and it's not very structured. Then I would say why don't you try INLA? It actually is formally correct by theorem when the data is a Gaussian process, and it's often effective, and it may be 1,000 times faster computing than MCMC. It could be much faster. And here's an ebook on it, and here's something in R on it, and here is an article by Rafael de Souza and his colleagues describing INLA for astronomy. And this article is not being read much. Many more people use MCMC than read this article. But this article is very good because there's a lot of problems in astronomy that are not so hard. And INLA is sort of the reasonable way of proceeding. But if you want to go ahead and do MCMC, you can, the results could be correct if you converged. For what I'll call moderately hard problems, the posterior surface is bumpy and it's complex, or the problem has a moderate number of dimensions, let's say 10 dimensions, and the likelihood doesn't take a CPU hour, but it maybe a CPU millisecond. It's not too hard to compute the likelihood. Then this is the regime where MCMC works really, really well, okay? Because it's too difficult to do with simple things like the EM algorithm, and it just works well, okay? You might want to experiment with a couple different algorithms, just what we're looking at with the pretty picture, the pretty app. You might want to experiment with different acceptance rates. You should examine diagnostic measures, the scalar measures, 2 or 3 of them, and some of the plots carefully for convergence. You should always do this, okay? And look at the pair plots, what we call corner plots, to map out and then you can interpret that. You'll say, oh, variable 5 and variable 7 are unrelated, it's circular, but variable 2 and variable 6 have a banana. And that implies that they're related to each other in the statistical model, which maybe has some fascinating astrophysics in it, all based on your data. If you have a very hard problem, so the posterior surface is very bumpy and crazy, and there's peaks in all sorts of places in the space, or the problem has very high dimension, 1,000 dimensions, 100 dimensions, or the likelihood is very difficult to compute. Maybe it takes a CPU day or a CPU year to calculate the likelihood. Okay, that you just can't do this. MCMC is just too much. Okay. And if you try it, you may not get the right answer. So what some recommend is that if you're stuck in some mode and there's other modes you want to map, they try annealing MCMC. It's analogous to simulated annealing in optimization algorithms. But what really happens for these very difficult problems is you have to give up calculating the likelihood correctly. and you make an approximation to the likelihood that's much easier to compute. And there is a procedure for this called ABC, approximate Bayesian computation. And in the last few years, this has now begun in astronomy. So here's one in cosmology by Yoshida, Cosmo ABC. Here's one here. Here's one in exoplanets. Here's another one in cosmology. Here's one in extragalactic astronomy. and there's more. This is not all of them, but it's mostly in the last few years, and it's, in my opinion, quite difficult. I've heard a lecture or two on this, and I find it difficult to understand. It involves hyperparameters for the priors. There are hyperparameters associated with the approximation. There might be other hyperparameters associated with the priors, and it's sort of a multi-stage calculation. It's quite complex. But some of the problems being addressed in exoplanets and cosmology and galaxies are so complex problems that normal MCMC doesn't work. You just can't do it. And this ABC approach is probably the best way. And I would do this with a statistician. And there are statisticians who are joining these groups. They're collaborative groups who do this together. And that is my last slide. I ended with some slides of advice. So I'm sort of sorry that I'm not really an expert either in stochastic processes or in MCMC. So this is not my very best lecture. But I think that hearing it from a non-expert, you then may hear it again soon, later on today, from more expert people who are actually doing it. And then a combination of my sort of foundations lectures and the more useful, practical activities that you're getting later today, I think. My hope is together these will be worthwhile. So that's it. Thank you very much. Are there any questions or comments about the last part of this lecture?
Okay, thank you, Eric. So I want to invite the participant. Maybe Nimas, do you want to ask something to Eric?
Yes.
Okay, go ahead.
Hello, Eric.
Hello.
Nice to meet you again.
Yes.
We first met in Thailand 2 years ago, I think.
There we go.
Okay, I want to ask about the best way to know about algorithm, the best algorithm that we must use for MCMC. Is there any way to know, or we just trial and error, or there is a way in statistics?
Okay. Basically, no, there's no way to know. there's no rule, there's nothing to maximize, there's no, yeah. What there is are people with experience.
Oh, okay.
Okay, and they're very valuable, these people with experience. Both statisticians and now some astronomers. Okay. So this package in R called Laplace's daemon, he has a very long vignette file, which really means a description of the package, where he discusses each one of these, about 40 of them. And in each one, he sort of gives you some hint. He says, well, this one tends to be good for this kind of problem. And this one tends not to work for that kind of problem. But even with his hints, I'm not sure I would believe that necessarily. And there is some progress. The early Gibbs Metropolis Hastings is not as good and as quick as the later ones, the more recent ones. And so the more recent ones tend to be more efficient, like the no U-turn and the Hamiltonian and the adaptive methods often are more clever than the early ones. And sometimes the choice of algorithm is, for difficult problems, is huge, has huge effect. A better algorithm may be 100 times better than another algorithm. Not just a little better, but much better. So let's take a look. How are we doing here with efficient nuts compared to the other one? And I think the answer is, it seems to be more efficient. It's doing the dense part and the thin part, and it seems to do a somewhat better job than the other one did. But each step takes more calculation. You can see all those wiggles. So it takes computing time to compute those curves and to make the next step. Whoops, I lost it. Oh, well, I think I stopped it by mistake. Okay. So the answer is essentially, no, you don't know which one to use.
Okay, I will try maybe
But for problems where the posterior looks relatively simple and you think you've done it, then it doesn't matter. They'll all do a decent job for simple problems.
Okay, thank you, Eric.
Okay, thank you, Nimas. So is there any question from the participants? Oh yeah, Eric. What is your suggestion about how to guess the best initial condition, especially for to run MCMC?
One possibility is to take out the prior and just solve it as an MLE problem using the EM algorithm once, not iteratively, no stochastic, just go up the mountain once and take that as the beginning. But the risk is that that may not be the only peak. It will be a peak, and it may be a local peak, and maybe not a good one. So another one is to take chains that are widely distributed and waste a lot of computer time way out of where there's no interest. But then you're more likely to sort of capture things that are far away or bumpy, and each chain then sort of does it. So a lot depends on whether or not the posterior that you're modeling is smooth, then it's easier, or if it's bumpy. And multi-nest claims it's better at bumpy, and maybe it is. And simulated annealing methods claim they're better at bumpy. Maybe they are. So the bumpiness, but frankly, from my perspective, if it's really full of bumps of similar size, I don't even think you know how to interpret. It's not even clear you want the peak. Maybe what you really want is to just look at it and say, well, my goodness, my problem has 3 separate solutions. This sometimes happens in X-ray astronomy, which is my research field originally. You get this X-ray spectrum that has not too few soft X-rays, and then a lot of medium X-rays, and then not too many hard X-rays. And so the choice is, there's an ambiguity of it's either a hot temperature without much absorption, or a low temperature with a lot of absorption, and nothing in between. There's 2 totally separate solutions, which maybe give a good chi-squared. We usually use chi-squared, and not Bayesian fitting, but they're quite different. They're totally different implication for the astrophysics. The one may be 10 times more luminous than the other. So that means we don't know. There's the galaxy or the quasar or the accretion stars, whatever it might be. We don't know the luminosity. Is it high or low? Because we don't have enough data to confine to decide between the two separated solutions. And generally speaking, if you get more data, you get more photons, it usually prefers one peak over the other, and then it becomes clearer. But because the shapes, the astrophysical shapes are slightly different. But if you only have, let's say, a couple hundred photons, you may not know which one it is. And you're left with scientific ambiguity. So I think if you have a multimodal posterior, you want to know that scientifically. And you might be just as interested in the other mode as this one. This one may be a little higher, but they're both interesting, maybe. You know, that's up to you as a scientist, what to do with your posterior. Choosing the mean or the mode or median is not necessarily what you want. Maybe you want the posterior to think about. There's a group of astrostatisticians, actually, at University of Washington who are saying this about photo redshift, photo Z estimation for LSST, the new giant telescope the American building. It has 6 bands, 6 numbers for each object. And often there's an ambiguity. Is it a low redshift galaxy of this type or a higher redshift galaxy of that type? And there may be 2 solutions or a big broad distribution. And so people say, well, just tell me the answer. And Jelko Ivichik, who's very distinguished, he wrote the book on the Python book I mentioned in my first lecture. He says, I don't think you should summarize it at all. We should just give them the function, the probability distribution function of possible redshifts, and let the scientists figure it out.
I see.
So there's there's 3 levels to these complicated things. Okay, there's the science question, then there's the statistical model and statistical method, and then there's the computational aspect. MCMC is only computational. And then Bayes' theorem and what goes into the likelihood and the priors, that's statistical. But that has a foundation in the science. And then when you get the data and you put it through the model and you calculate your MCMC, you get this posterior. You have to go back and think like a scientist.
Mm.
If it's simple and has a single peak, then it's easy. There's just a maximum and a best value and I'm finished. But if it's not simple, then you have to, you either give up or says, I don't have enough data to answer my questions. I'm just going to walk away and do something else tomorrow. Okay, people are not doing that enough. People don't realize that sometimes your data don't allow you to do your science. So the way science is, you cannot answer every question with every data set.
Yes, of course. Okay, thank you, Eric, for your comprehensive answer. Okay, maybe we already met the end of the presentation. So yeah, thank you, Eric, for your wonderful lecture. We are glad to have you in our school here. And then maybe I wanna, yeah, I wanna invite the participants to open the camera and give applause to Eric. And then we have a photo session at the end of your lecture. Oh, maybe is it okay for you if there is some question from the participant by email or something?
Sure, absolutely. I don't think I gave you my email. You can give them my email.
Oh yeah. Okay.
@psu.edu. And just tell me who you are and tell me that you met me in August at the ITC, you know, at Bandung. None of us went to Bandung, but we are all there. You're all hosting us. So just tell me that who you are and then ask a question. I do consulting, you know, sort of all the time. It's sort of, to be honest, I prefer to talk to you when you're beginning and when you submitted a paper and then I see it as submitted to the journal as an editor, And sometimes I say, gee, they should have spoken to a statistician a while ago, because a statistician would have said, you should do something else or try something else. So I'm very pleased to consult with you.
Okay, friend Eric, very welcome to discuss with you all. Yeah. Okay, thanks, Eric.
And I want you to know that I am impressed with Indonesian astronomers, that you have so many and that you're so young and you're doing so much. So I congratulate you in doing this. And statistics is a wonderful thing that you can do without a space program, without a lot of money. You can do statistical astronomy in Indonesia as well as anywhere in the world. So I'm glad that you're learning this today.